Whoa, okay. So good morning or afternoon or whenever you're watching this video. Today I'm going to do another titration lesson. This one is going to be an oxidation reduction titration. And so we're going to work through a sample problem and kind of talk about what we would do in lab to get all the data that we need to solve the problem. Okay, so you need to make sure that before you are watching this that if you haven't been to class, make sure that you have read the titration notes, which I'll show you again. You have a copy of it. It's in Schoology. Make sure you look through the titration PowerPoint, watch the other titration lesson video, the previous video on titration. So make sure you have an understanding of what titration is as a lab technique, okay? So let's get into the problem, okay? So here we go. All right, so again, these are the notes I'm talking about, so make sure if you haven't read over your titration notes, here's a sample titration problem. You should read over that. As a redox problem, a redox titration problem. So make sure you look over that and got that going. All right, so let's look at today's problem. All right, so our problem, we have a sample of iron ore, and we want to determine how much iron is in it. What's the iron content? Okay, so we want to determine the percent iron in this ore. Okay, so for those of you asking what ore is, okay, Google it. Here, I'll show you. What is ore? There's gold ore, there's iron ore, there's copper ore. So what's iron ore? A rock with iron in it. There you go. So there you have it. It's a rock with iron in it. And we want to know how much iron is in our sample of ore. Okay, so that's our idea. All right. So if I want to find the percent iron, it would be the mass of iron in the ore divided by the mass of the ore times 100, right? That'll give us our percent by mass. So we have the mass of the ore, so we have that number that we would put down there, okay? So our goal is to figure out how much iron is in there, okay? So obviously we have to separate everything, right? We have to separate the iron from the ore so we can isolate the iron and figure out the amount of iron in the ore, all right? Okay, so what we do is, remember kind of what we did in our brass lab. What do we do to separate the zinc and the copper? We actually dissolved it in acid, and the copper and the zinc both oxidized to +2 ions. All right, so that's essentially what we're going to do here. We're going to take our ore sample and we're going to dissolve it with excess hydrochloric acid. And so our resulting solution is we're going to have all the other inert rock materials that don't react with the acid. So they'll be floating around, but we don't care about those. What we care about is that we have iron 2+. So all the iron, all the solid neutral iron that was in the ore has oxidized to iron 2+. And because we have excess strong acid, we have a lot of H+ in our solution. Okay, that's going to be important, based on the fact that we know that the redox reactions that we're using for redox titrations either have to take place, or they only take place in either an acidic solution, so where you have a lot of excess H+, or a basic solution where you have a lot of excess OH-. So in this case, our resulting ore solution, so we took our piece of ore, we put in a bunch of acid, all of it dissolved and reacted, and all the iron that was in the ore has now been turned into iron 2+ ions. And but since we had excess HCl, we still have, this solution still contains a lot of H+, okay? All right, so now, you're going to be given access to some things. Okay, so we took our ore, we dissolved it in acid, so this is our solution. And our goal is now to figure out how much of this is in the solution, because all of this iron 2+ came from our ore. Okay, So if we can figure out how many moles of iron 2 plus are in here, then we could easily figure out how many grams, and then we'll grams of iron divided by our mass of the ore times 100, and we've solved our problem, right? Okay. So what are we given? We're given a 0.05120 molar solution, moles per liter, of potassium permanganate. We don't care about potassium. We just care about the permanganate. Potassium, remember, alkali metal ions are always spectators, okay? So we don't care about that. So really, because the subscript of permanganate ion is 1 in this compound, really, this is what we have. We have a 0.05120 molar solution of permanganate ions, okay? And what we need to know, and moving forward, and you'll find out when we do our lab, is permanganate is purple in solution. So even if you just have a little bit of permanganate, your solution is going to be purple, okay? And the more, and just like we learned in the copper lab, in the brass lab, the more permanganate you have, the more light's going to be absorbed, the more darker the shade of purple is going to be, and that kind of thing. Okay, but it's important to know that permanganate is purple if it's in solution. Okay. All right, and now we're also told that permanganate will completely react with iron 2 plus in an acidic solution. I didn't write that down here, but it needs to be in an acidic solution according to this reaction. So notice the H plus there. So this reaction will go to completion, meaning if there's any iron and any permanganate, it's going to react and it's going to turn into this. So let's just look, let's understand. We know that whenever we do a titration, we need an indication when the reaction's complete. So let's kind of imagine what we're going to be doing here, right? We have our iron 2 plus solution that we made by dissolving our ore in acid, right? And again, we have H plus, and we have chloride, and we have other stuff that dissolved from the rock, but all that other stuff is inert, so we don't care about it. Okay, so we know that in the solution we have a bunch of iron 2 plus ions, okay? And what we're gonna do is we're gonna slowly add the permanganate solution to it, and so the permanganate and the Fe2 plus are gonna react. But what's going to happen when we run out of iron 2 plus? Well, we'll add permanganate, but there won't be any iron 2 plus to react with, so the permanganate will remain in solution. So if we can imagine what's going to happen is, this solution, let's say, is colorless, okay? When I add permanganate, it turns purple because permanganate's purple in solution, but as soon as the permanganate reacts with the iron 2 plus, it goes back to clear because the permanganate gets taken out and turns into manganese 2 plus. So I add the permanganate, the solution turns purple, but if there's iron in it, it'll react and it'll go back to clear. So the solution will turn to purple, but then if there's still iron in that solution, it's gonna go back to clear, okay? So what we're gonna be looking for in our titration is we're gonna slowly add the permanganate, and we'll be making sure we're stirring the solution the whole time. So to give all the permanganate a chance to react with iron 2 plus. And so what we're looking for is when we add a drop of permanganate, the solution turns purple, and then we kind of swirl it around for a little bit, and it goes back to clear because the permanganate reacted. And then we add one more drop of permanganate, and the solution turns purple and stays purple, no matter how much swirling we do. And that's our indicator, that's our indication that all the iron 2 plus has reacted. Okay? All right. All right, so again, what we should do is slowly add the permanganate solution to our iron solution until we see the indication of the completed reaction. And in this case, because the permanganate's being taken out, we're gonna see purple to clear, purple to clear, purple to clear, purple to clear, and then all of a sudden it stays purple. And when it stays purple, that's when we know our reaction's done, okay? So again, as long as we have iron in the solution, it will take out the permanganate. Once we run out of iron, the permanganate will remain in that solution that we're analyzing, our analyte solution, and it'll remain purple. So our indicator, one drop of permanganate, solution stays clear, and then one more drop, solution stays purple. Solution stays purple, that's our indication, reaction finished, okay? So in order to do our calculation later, we need our balanced redox reaction. So if you follow your steps for an acidic solution, you should be able to balance this reaction. And this is the balanced reaction. And so what we needed to figure out was this ratio, 5 to 1. So for every 1 mole of permanganate that reacts, we know that 5 moles of iron 2 plus react, okay? So we needed that ratio here for our calculation once we're done with the lab, okay? So our procedure would be, we would load our titrant solution, which is, again, the titrant is what we know the concentration of. We would, and that's the permanganate solution. So we would load our burette with our known solution of permanganate. And, you know, make sure you follow the procedure. You should always do an initial rinse with your solution and then load it, right? Don't rinse it with distilled water and then load your burette. Make sure you do an initial rinse with the stock solution and then load your burette. Okay, great. And because this is a titration, you don't know how much of this solution is going to be required, right? It could be all 50 milliliters. So whenever you're doing a titration, you know, it could be 1 drop and you're done, but it could be 50 milliliters and you're done, right? And if it ends up being more than 50 milliliters, oh no, you're out of luck because that's all your burette holds, right? So since you don't know how much of this is going to take, load your burette all the way to the top, so where it says 0.00, okay? So you would take your initial reading, and again, whenever you do a titration, you want that 0.00 for your initial reading, okay? Because you don't know how much it's going to take. All right, and then what we would do is we would have our ore solution below the burette, and we would slowly add the permanganate solution to our ore solution, okay? And we would keep adding it until we got that indication, right? So, you know, at the start, it's going to go from clear to purple to clear very quickly because you have a lot of the iron. But as the iron gets used up, you might have to stir the solution a little bit more and more and more for it to finally go from purple to clear. But again, we're looking for that one time, boom, where the solution was purple, and then maybe we stirred it a bunch and it went away, it went back to clear, okay? Okay, and then once you get the indication that, you know, you add 1 drop of the permanganate, it turns purple, it stays purple, you know you're done with your titration, and you would take your final reading of the burette. So I'm just making one up. So let's say, you know, we loaded our burette to the top, so 0.00 was our initial reading. And let's say we got our indication point that the reaction was over at 31.6 milliliters. So that's our final reading of a burette. And remember, your burette reading should always be 2 decimal places, okay? And then so that's all you would do in the lab, you'd be done. So now it's cleanup time, okay? And then after you're done with the lab, the calculation you would do is this, right? So you would figure out what volume of the permanganate solution was required. Now, again, it was potassium permanganate, but we don't care about that potassium, right? So yeah, we had in our final solution that we made, as we add the permanganate solution to the ore solution, there's potassium ions in there. But we don't care about them. They're just spectator ions. All right. So we found that it took this volume of our permanganate solution. And remember, now we have the volume of permanganate solution and we knew the molarity. So we could figure out how many moles of permanganate were required to react, right? And so now it's just stoichiometry. We would do liters times the molarity of the permanganate. That would give us moles of permanganate. And remember, our mole ratio for our balanced equation was 5 to 1. 5 moles of iron 2 plus for every 1 mole of permanganate, right? So again, I'll go back up to our balanced equation, 5 to 1, right? So we know the reaction that is happening, and we know it's a 5 to 1 ratio. We just figured out how many moles of permanganate reacted. So times 5 divided by 1 would give us how many moles of iron 2 plus were in our solution, okay? And then that's gonna be moles of iron 2 plus. We multiply by the molar mass of iron, and that'll give us the grams of iron that were in the ore. We divide the grams of iron in the ore divided by the mass of the ore. So remember, this was the mass of our rock that we had. and we multiply by 100, and we get our iron content. So our piece of ore was 10.68% iron. We did it, okay? And that's all it is. So all the titration is the lab technique to get the data, but then what you do with the data is just stoichiometry. All it is. That's all it is. That's all it is. So in this case, if we follow our steps, take what we're given and convert it to moles, what we were given, a molarity of permanganate and a volume of permanganate. So we convert it to moles. We multiply by our mole ratio, okay, which we find in our balanced equation. And then we convert to desired units. Now, desired units in this case wasn't just grams, it was percent by mass. So we convert to grams, and then to get percent by mass, we take our mass of the part divided by the mass of the total times 100, and boom, we got our desired units, percent by mass. Okay, and then we say boom, baby, and we did it. Okay, so hopefully that helps you with the assessments and Schoology and stuff. And remember, we're going to do an acid-base titration lab coming up here next week, and then followed by a redox titration lab, okay? So you'll be able to practice, actually do this, but when it comes down to it, when it comes down to test questions, all it is stoichiometry, right? Because you can't do the lab on the test. All you can do is know what to do with the data, right? So what kind of data do you need to take, and what is the calculation you do with the data? And again, it's just solution stoichiometry, okay? So, yep. So that's it. I'll be posting this in Schoology. Hopefully you watch it. Obviously, I don't know why I said that, because if you're watching the video, obviously you found it in Schoology. Okay, anyway. I don't know. It's early. Have a great day. Keep always thinking about chemistry. Always. Do the bonus of the day. A lot of people aren't taking advantage of that. I mean, it's a good way to just have chemistry on the brain at least once a day. At least once a day. Okay? All right. Later.